this is sort of a coincidence map. So you see here that this is the time of flight of the first fragment, this is the time of flight of the second fragment, and then you see that all the correlations in a time of flight, whatever the correlation that you have missed, so you do not know whether this edge is a different energy, what this edge is. This coincidence maps gives you a full structure of what is the dissociation partners and how the energy is correlated among the dissociation partners. So you see here, if you have a nitrogen forward and backward, you see here there is an island. If you have nitrogen plus, first hit of nitrogen 2 plus with second hit of nitrogen plus, you have this island, and then for nitrogen 3 plus with nitrogen plus, you have these islands. So in the time of flight, you do have these kind of edges where you can fit kinetic energy release distribution, and then find out a kinetic energy like this is almost immediately visible in a coincidence map. Now what you have to do is that you can grab this part, which we call it as graphical cut. You can cut this part, project it along your time of flight axis, and you get the kinetic energy release for every dissociation path. And this is the beauty of this coincidence map. Okay, now this is just in time. Think about that you not only in time, you do have the information of every partner in x and y also. So you have momentum px, py and pz, all three of them for every partner. For only pz is your time of flight, and this is a coincidence map of only, you can say, pz component. But x and y is also there, and we have to take care of that because that gives you a picture of what is the molecular dimension or what is the molecular structure formed during dissociation. So we need all of that. But this coincidence map is good enough to do that. One thing will always come in your mind is that why does the coincidence map always have this slope? And I will tell you that when you don't have it. So why does this coincidence map always have this slopes? See, you can say a negative or this may be a positive. Why this slope? That is, you again go back to this simple picture that you have one going forward and one going backward. Now if you go back to here, the picture, so this is a coincidence map between nitrogen and nitrogen. Okay, this every dot of this coincidence map, don't take these lines because they are noise, but every dot inside this coincidence map, see, this is a coincidence map of nitrogen versus nitrogen. So the nitrogen molecule breaking apart, both of them are nitrogen plus. So only a first fragment of nitrogen forward, means whatever is going along the time of flight will have a coincidence of whatever is going backwards, right? So nitrogen forward coinciding with second hit of nitrogen backward. Okay. And over here you see this coincidence map looks like that. So this nitrogen 2 plus backward, so B is backward. Backward means going against the field. So nitrogen 2 plus backward in coincidence with nitrogen plus forward. Okay, because there is only 2. So either what nitrogen 2 plus backward will coincide with nitrogen 2 plus nitrogen plus forward, or nitrogen plus backward means nitrogen plus backward coinciding with this guy, which is nitrogen 2 plus forward. So when you break away from a central spot, one thing will go along the field, one will go against the field. And therefore, in a correlation, the forward comes with the backward always, because the masses are still the same. Only thing, because of the kinetic energy release, you are having this spread in time of flight. They should come at the one part. If there is no kinetic energy release, you will just get a dot, just a spot. Now you are getting a spread because of kinetic energy release, and one is going along the field, one is going against the field. So it is always the forward with the backward. And if you plot that forward with the backward, you will only get slope in this way. Only the slope which looks like, you call it minus slope, right? I'll tell you. Yeah. I'll come to that. So, okay, I have discussed a lot about this, so I will just skip through that. Only thing is that from the time of flight, if you get, you can actually get all the momentum vectors, and this is like the famous Rondeck delay line detector thing. So, only thing is that if you, this is a microchannel plate, and behind the microchannel plate, you have this delay line, which is a fine copper lines wound up. And then if a fragment falls on this, so this is a position sensitive detector, whatever the fragment falls on that, if the fragment falls on that, you know what the MCP does. It has micron pores which is coated with a material which has very low work function. So even if one particle, electron or ion, even photon, if it falls on that, from one hit on that material, on that micron pore, it ionizes, or it actually multiplies the electrons released from that. And for one particle, you get 10 to the power 5 to 10 to the power 6 number of electrons. So you see here, this is a channel, a charged particle falls on that, and it gets multiplied, and the electron is released. Because it has very low work function, electron is released, and then this electron hits along this, hits along the pipe. Okay, hits along that micron channel, and every time it hits, it releases more and more electrons. So at the end of 2 millimeter of these channels, you get for one particle 10 to the power 6 electrons. So it's a 10 to the power 6 electrons means it's a huge charge. And this huge charge, after it comes out of this MCP, at the end of the MCP, you have this copper lines. So think about, this is the copper line which is wound, and you have a charge over here, the huge electron cloud. So if this electron cloud would break away, this is actually called a kind of transmission line. The electron cloud will create, there is a voltage on this line, and due to the electron cloud, it will have two pulse, means just a drop of the voltage, and it will flow in two directions. Okay, one part of this transmission line will be recorded by a timer which is at the one end, and the other part of the timer will be here. Okay, so if your cloud has fallen in one direction, in one side of this helical delay line structure, the pulse from one side, shorter side, will take lesser time, but the pulse from the longer side will take more time. Okay, so see about that. This takes lesser time, this takes more time. So depending upon where this electron cloud has fall, if you subtract T1 minus T2, you can get from the time the position. Did you understand that? Okay, so you subtract T1. So if this cloud has fallen just here at the edge, this T1 will be very small and T2 will be very large. So from that T1 minus T2, modulus of that, you can actually find out where your projectile has hit. So this thing, for every fragment or every event, you have to detect. And that comes to the question, why your rate, coincidence rate for event has to be low. Because if there is any other cross section, if there is any other event from a separate molecule comes inside this, your entire structure gets jumbled up. So we had to keep our coincidence rate low. So we don't say data acquisition rate low, coincidence rate low. So even if we are taking like 5,000, we always find out, we always collect data, and then we run our analysis and then say how much coincidence did you get. And if you say that, okay, I have collected 1 lakh of events, but my coincidence rate is only 10,000 or 1,000. Oh, no, 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 you have to drop things down. You have to be careful on that. Or else you are just wasting your your beam time. Okay. So yeah. Yeah. These all black patches. These are true coincidences, but this you see the black patches as well as line which is perpendicular to this. These lines. These are all false coincidences. Your map will be dominated, yeah. Hmm, hmm. No, yeah, yeah. You did a beam time. You are not very careful, or sometimes even after careful, you have to clean up. So what we do is that what you can do is that now you look for. Now there are different ways to do that. You have a data set. First, you run your data set that my molecule is triatomic OCS. So I only take those events where there are 3 hits. Okay, this reduces the other background that I need only 3 hits. When you get all the 3 hits, then you look at the coincidence map, it will be a lot cleaner because you are selecting them. Now the point is that even then you will have a lot other events which is 3 hit but not in coincidence. Then what you do is that a simple fact is that you since we are detecting X, Y and Z, Px, Pz and Py, all 3 of them, what we do is that we calculate the momentum, means you can do it by this way. So you calculate the momentum of all 3 events and then you add them up, buying positive or negative, you add them up and we see that the momentum balance is across 0 or not. Sometimes because since our interaction volume is bigger, the interaction can happen anywhere. Sometimes it happens that the ion beam is moving and the jet is not very localized. If you have a cold jet, it is a lot localized. If you have an effusive jet, it is really spread, like 5 millimeter it is spread. It is denser jet, but then it is not localized. And cold jet means it's a lot of money, it's a lot of alignment. Not every lab has it. None of them are from cold jet experiments. But then what you do is that you have a dissociation event over here and over here, because along the beam path you are dissociating molecules, right? So there everything breaks apart. So whatever, even if you are dissociating earlier or you are dissociating later, you are only catching those 3 events from a single molecule. So you do a momentum balance among them and then fit it so that you see that what is your whether the momentum summation comes to 0 or not in X, Y and Z, all 3 of them, right? If you get a spread, the better is that you then cut along the central part of it, which is very close to 0. Then whatever your interaction zone is, at least you know that all fragments came from that spot. So it's like Diwali firecrackers, that you came like this or you came like this. You do a momentum balance on this guy and momentum balance on this guy. Okay, separately, event by event. And then when you add them up, it will all come Px 0 or Px, Pz and all those things around 0 or not. You might have a spread there, but then if you are selecting the central part of that, you know that yes, I have a very correct coincidence events. But then you also cut down your number of events. So your signal to noise ratio also comes down. But we had to do those tricks because my guide once said there is no perfect experiment. This broke down. So this is some kind of some kind of, so it's not going back and forth, so I'll do it from here. This is some kind of time of flight and coincidence map that you get with position and time of flight. Now what we can do here, what we can get from here is the angular distribution of fragments in a molecular reference frame. All this information comes very handy and comes very, just comes on front of your eyes. The bond angle at the instant of dissociation, because now you have both three momentum vectors together. And the energy release also, the distribution also you can find out. Now let me give you a different case where whatever I have done, whatever I have told you got mashed up. So do fragments always dissociate along molecular axis? This was the question. That now I come to the research part. I tell you what real life situation happens. So does always a linear molecule, say like there are many hydrocarbons, say C2H2 and C2I2. These are like simple four-body systems. Okay. There are many hydrocarbons in space. Sometimes there is ion molecule interaction happens in space, where there are intermediates which may act as precursors, because there are, if you do a spectroscopy of the space relevant molecules which has been detected, sometimes you get just fascinated that how come this bond structure actually happens. Is it possible to make that molecule here in the lab? Your chemistry will say no. How can you really leave out these bond, and how can you have a fractional moiety which does not come into any stable structure, any bound state, but you do detect them in space. So what our idea and what we usually try to do is that what is behind the reason of such molecular bonds or such molecular fractions that you detect in space. There are probably 300 molecules in space. So we took one simple molecule is like acetylene and C2I2, the four-body system, and then replace these terminal atoms of acetylene with a light hydrogen. And then with a heavier iodine, we wanted to replace the hydrogen with iodine and repeat the same experiment. Okay. Just to see that is there any effect of heavier terminal atom, that is iodine, on vibrationally active bending structure? Because this is a non-rigid multiple charge molecular species. So everything while falling apart, does this iodine play a role, this terminal heavy ion? Or whether this breakup dynamics of Ci in C2I2 bond differ from CH bond? Is the breakup sequential or concerted? How do the breakup, is both of them have breakout in the same step or separate step? And whether there is bending motion on the structure, because does it remain linear at all? So all these things we wanted to study, and we first studied this momentum map of dissociated acetylene molecule. All the time I have said my coincidence map should look like that, but it doesn't. Okay, so of course not every coincidence map look like that. Here you can see one of them is not even forward backward, it is just straight flat. How come that be? One of them is not, there is forward backward, but there is also forward backward. This question somebody asked, how can that be, right? So when we got this data first, at least in my PhD, we were like really shocked that what we are looking at. But then you find out that this coincidence map, what is given you is that this is a momentum contour. The entire velocity pattern, the momentum pattern is seen over here. So you debug one by one. You see, when you have these kind of structure, it is like one going forward and one going backward. But first thing is, what happens when you have straight like that? So this forward and backward, this exact forward and backward 45-degree means you have a two-body fragmentation channel where the momentum is completely balanced. So this charge and momentum, the angle between them play a role that you see in the coincidence map. And if you have equal momentum, then it is exactly 45. But then what happens to this one, which is C2+? C2+ means, see, this is acetylene. So you have carbon-carbon at the center and hydrogen at the end, right? So this is carbon-carbon center and hydrogen. So whatever you get this, whatever you have this angle, if you project this on the time of flight, you get a kinetic energy release. right? From the kinetic energy release, I went to the momentum map. So if I go back, this is the good part about having a tutorial, that I can go back. For a conference, I cannot. So here, when you started with a time of flight, this exact time of flight is a momentum map or not? You might have a question. So see here, these are edges over here, and this is the time of flight. The same time of flight, momentum map is nothing but whatever the projection you have in the time of flight, this is only this part. Now you see, there are two kinks over here, right? This is a shoulder over here. This part comes from, so this is a shoulder over here, you can see over here that this shoulder, this part, the central part, comes from n plus n plus. The next part, this shoulder, comes from n plus n2 plus, and the edge over here comes from n plus n3 plus. Okay, so the momentum map gives you a kinetic energy release but separates out the every dissociation channel. Now you come back over here, that this also gives you a kinetic energy release. So this is a kinetic energy release on this side and kinetic energy release on this part, because there are two fragments, H plus and C2H plus. But then what happens to this guy, C2 plus? You see here, the hydrogen has a maximum kinetic energy release, but C2 plus is very narrow. So almost no energy is imparted to C2 plus. You get a lot of energy in the hydrogen. That actually means that while breaking apart, the two hydrogens have broken apart at the same time. If you have two hydrogens breaking apart, the only C plus stays there and it does not move. So it's some kind of a concerted thing. If at least one of them breaks before, the other one will be pushed. But here both breaks apart at the same time and the central part does not move. That's why you almost, if you project this C2 plus on this channel of the second fragment, almost no kinetic energy. Of course, in the kinetic energy, while calculating the kinetic energy, you have to calculate time and then correlate with the mass. Then only you get the energy. So here with this mass, no movement at all. Okay, so the central C2 plus did not move at the hydrogen breakaway at the same time. Now, the other part of it. Diatom behavior, that is, these carbon-carbon, if you are looking at carbon-carbon correlation, what happens is that this is breaking apart, and this is, if you calculate this momentum map with the different charge state, like channel C plus, C2 plus, okay, 45 degrees, 63 degrees, you can calculate the slopes if you have different charge states. And exactly those kind of slopes, so this is the slope that I am plotting, exactly those kind of slopes that you are getting here. But this is not a diatomic molecule, right? This is actually a 4-body. So the first picture that I showed here is that hydrogen is breaking apart one shot and C2 plus does not move. But it's not only true. If you doesn't have C2 plus but C2 double plus, hydrogen breaks apart fast, and then the CC bond takes its own time to break. And this breaking is delayed in a time. That's why this breakaway is like a diatomic molecule. So exactly what slope you should get by nitrogen plus or nitrogen plus nitrogen 2 plus, you are getting by C and C. So it shows that yes, if they break at the same time, things will be different. This broke away at certain times, means the hydrogen broke away, the central C was still not broken. After that, when the central C broke away, it does not have any effect of hydrogen. So it's like diatom breaking, C2 molecule breaking away. But what happens to these complicated butterflies? Now this is what you have probably said, like what happens if both the fragments go at the same direction. Now see, the story is that it's like H plus is breaking and C plus is breaking, right? What happens if the opposite happens, that the CH bond breaks first? If the CH bond breaks first and the C and H, these two break at a later amount of time, these already have a velocity in one direction. So if you go to your time of flight, and I have told you that one fragment is going along the time of flight, one fragment is going against it and then turning around. But if both the fragment has broken this side, both the fragment is going together and at a later time they to break. So you already have a velocity in the direction of the time of flight and then they break. So you see here that this is forward backward and this is backward forward, which we usually see. But if both fragments break together and you detect these carbon and hydrogen, they both are forward forward here. So they'll take lesser time. This is the one, so this is the hydrogen plus time, this is the carbon 2 plus time. So this guy takes less time than the hydrogen center. So this comes earlier than hydrogen and the carbon also comes earlier. So both break together and flow in the one direction. Then you get forward forward. If they break and they break against the electric field, so if this is the extraction field, this gives forward forward against the field, then both of them goes in the other direction and both of them turn around. Then you get backward backward. Okay, and if one forward and one backward goes around, these two are, you are not detecting them. It's not that they are lost. So these two we are not detecting them for some reason. So forward and backward, carbon and hydrogen can be forward backward. We get the usual case. You probably cannot, only a femtosecond laser and a pump probe spectroscopy can give you an idea. See the but yeah, exactly, that has actually happened. But if you talk about time scale, the problem is in ion beam collisions, you are only looking at the final what you can result, but you're not looking in time frame what is happening in between. You can only speculate things by looking at the final results, and everything is open, all possibilities are open. See, all three possibilities are open. But if you use like femtosecond pulses and a pump probe spectroscopy, then you can probably tune to particular dissociation patterns, and that is the beauty about doing the femtosecond spectroscopy, which you cannot get a time resolved thing. So I don't know whether how good time I have. Almost up, so I'll wrap up fast. Okay. So the story for C2H2 is good, but as soon as you go to C2I2, the entire coincidence map doesn't even have a butterfly, now it becomes donut. So even more complicated, and we are still analyzing this. You see here. So you can easily see that it does not happen in the way that you should think about. So in acetylene, you said like this is a linear molecule, the hydrogen are weaker or they are lighter, so they should break apart and the carbon pushes them out. But the iodine completely changes the scenario. You have two big atoms of iodine sitting there, so even if the carbon wants to go away, there is no way. And iodines are so heavy that it's sort of like the carbons are trapped in a barrier. They are trapped in a wall because of the iodine, and so they probably have done multiple collisions and found their way in some angle. Just like here. But we do not know the angle we are calculating. It's quite a big spread of angle that you see here. And so the donut shapes change when you just by hydrogen you change it to iodine. Now, as I told you that for a single capture, you do have a possibility of seeing a molecular frame at very high charge state. So even for C2I2 3+, we can see that the triply charged molecular ions stay stable. Okay. And there is also a calculation being done where they expect that even quadruply charged can be stable. collisions lead to isomerization. This is one of the spectrum we probably never published. But yeah, isomerization is sort of like one hydrogen moving from one side of the molecule, acetylene molecule, and going from the other side and making a CH-CH bond with one carbon. Okay, this is isomerization happens in many natural processes, and it is sort of like it's either a heavy bending mode which just forms one hydrogen going on the other side, and we also saw isomerization for iodine, that C2I2 plus. So even with a bigger I2 plus, there are stronger bending modes where you can see this I2 plus. But yes, where I started and I said like that, does this highly charged ion do something, or even if you change the charged ion, will it do something? This I2 plus does not form if you have argon 8 plus, but it does form if you have a slow argon plus beam. So it's a soft collision that makes this molecule to bend and form this I2 plus. Not a very strong collision, not a very highly electric field. When it is very strong, the molecule probably breaks away into much higher charge states, and you do not get this finer details. But for argon plus, the impact parameter is low, the energy is only 50 keV, soft collision, the molecule tries to bend itself and then forms an isomerization. Okay, I have other stories, but let's stop here.
So I know that the group in Caen, they have measured ICD by ion impact. You know, I mean Cassimi and others. Right? They use the same apparatus as you?
Same?
Apparatus? So they have also...
Yeah, their apparatus is very similar. Yes, yes.
Okay. So what's the difference with their...
I did not follow the ICD. I'm not an ICD person, to be frank.
No, I'm not talking about the ICD. I'm really talking about your apparatus and their apparatus.
They are not.
Their spectrometer.
This is very similar apparatus.
It's the same idea.
Yeah, the Amin Kasimi and Jun Matsumoto, they are collaborators there. And so, yeah, this is the very similar apparatus.
Okay.
So, yes, you can do experiments by ion collisions.
Okay, thanks.
And also for synchrotron radiation, I think they have also seen ICD for synchrotron radiation with the photon impact. So to be frank, like I came here to learn about ICD.
Okay.
But then these are the tools which actually enable us to measure these nice processes. Yes,
for the sequential ionization, so that the slope is 45 degree. But for a concerted decay, if on neutral is released with so less momentum or energy, then also the slope will be 45 degree, almost.
If it carries the same amount of momentum. If it's balanced, then
suppose
only.
it is a three-body dissociation with a neutral molecule, neutral fragment, which has very less energy, kinetic energy, then the slope will be also 45 degrees, I think.
No.
It's not?
If the neutral one does not take too much of energy, then it will be still 45. But usually, like for a three-body, this simple picture does not work. For a three-body, I haven't discussed that. You have a Newton diagram or Dalitz plot we have to do. So there what happens is that you fix the momentum of one of the particles and you see what is the momentum of the other two. I mean, you can do with one neutral also.
Yeah.
If it is three-body. Neutral, the problem is that the neutral you haven't detected.
Yeah.
So you can speculate it is a neutral. You might speculate it is an ion. So what we do is that if it doesn't take too much of energy, then we say it is a neutral. If it takes a lot of energy, it's an ion. But if you can do experiments where you detect all three, that's complete.
Yeah.
So usually we do a momentum balance and we say what is the momentum left about is taken by that unrecorded fragment or unrecorded neutral, but you cannot really say it's a neutral. But at least for a 3-body. But when you go for a 4-body and you detect only 2 of them, you really cannot say whether those 2 are charged or neutral or whatever. So it's good to have detecting all 4 of them, and we are like lucky that we have a 120 millimeter detector for these donuts. So we got 4-body detection. That means you have a bigger detector. Other than that, you are not really detecting, because bigger molecule will have a lot of kinetic energy release. So you will definitely miss one of them. If the molecule is aligned like this, the one fragmenting here and the one fragmenting here are 2 parts of the detector. That if you have a stronger electric field, you are closing down, narrowing down this angle, but then you are losing in resolution. And you are, the more time of flight, you cannot have a shorter time of flight, then you are losing your resolution in m by q. So no other way. You have a moderate, I mean, you have to have an optimized m by q and a bigger detector. But that takes money. We might want anything, everything, but
the developments in detecting also neutrals in same experiment, of course.
well, energized, like we detect the photons, the energized neutrals can be detected with this kind of microchannel plate detectors. And Rondek has developed like that, detectors like this, where they detect the photons and the neutrals. UV photons are better detected. IR is also fine. But for neutrals, see, the whole point is that you have to initialize that one electron. So you need a momentum. So if the neutral is really of very low energy, you probably cannot get that one electron coming out from the pore, coming out from that channel. But if you have high energy neutrals, you do.
But if the neutral is excited,
Yeah, you can.
okay. So since that's not the case, but we're also heading close to lenses colloquium. So thank you once again, Shankar, for this very illuminating session. And thanks to both Nico and Shankar, as well as Lens, for chairing the session here. And I will, but that's your presence means a lot, Lens. So I will also certainly request you to honor the speaker with the present. Now it's.
Does he know what there is in
He can figure it out, because we revealed it in the morning. Right.
Thank you.
Wait a second. Yes. Absolutely. And like that with the audience, I can get one. Oh yeah, absolutely.